Welcome again for another session of Haskell Law. And this time with us we have, um, well, first we've been hearing talks about well-typed code. So now we have Andrew's Law from Well-Typed, um, and he has been using Haskell for over 20 years now, and has done his PhD studies on extending the Haskell languages with the language with capabilities for data-type-generic programming. As I mentioned, he is the co-owner of Well-Typed LLP, a special Haskell consultancy. He likes to think about how to apply functional programming to tackle real-world problems, and such is the talk he will give us today. He will show us how to get the most performance from our programs written in Haskell without having to sacrifice elegancy or precision in our code. So that means we can keep our highly abstract code and have it running performantly. So now I present you Andres.
Okay, thank you for the nice introduction. I hope you can all hear me and see my slides. So let's jump right in. So let's look at a Haskell program. So this is a data type of binary search trees. So these are simple binary trees where you have a left and a right subtree in the nodes. And we're fixing the keys to be integers, and the elements associated with these keys are of type A, which is a parameter of this BST type. And because it's a binary search tree, we assume that the keys that occur in the left subtree are all smaller than the key stored in the node, and the keys that occur in the right subtree are all larger than the key stored in the node. And then we have a completely standard lookup function on these binary search trees where we pass an integer key that we want to look up and the binary search tree, and we get a maybe A out. And as is typical for binary search trees, the interesting case is the node case, where we compare the key we're looking for with the key stored in the node. And depending on the outcome of the comparison, we're either continuing looking in the left subtree or in the right subtree, or on equality, we just return the value that is stored at that position. So now if we have a simple example tree that we assume to be statically known, so it's basically fixed in our program. This is just a simple example, but in a real life scenario, it might be much bigger, but nevertheless statically known. Then we can write a specialized version of lookup that fixes the table or the tree to be exactly this example value that we've denoted here, but still takes an arbitrary integer. And we can ask ourselves the question, will the tree be optimized away by the compiler? Now, the answer to this question is surprisingly simple, namely no. So if you look at the core code, slightly simplified, that is output by GHC, even with optimizations on, you'll essentially see that the call appears exactly like you've written it. So lookup table will be a function that takes an integer and calls the lookup function on the table, which I haven't listed here. And then the lookup function itself is still first performing a pattern match on the tree, on node or leaf. And in particular, in the node case, we do these comparisons, and we still call lookup recursively on the left or the right subtree, depending on the outcome of the comparison. So why not? Well, I mean, first of all, lookup is a recursive function, and recursive functions are never inlined by GHC. So even if you were hoping for inlining, just by the simple fact that lookup is recursive, that doesn't happen. Now, you could still hope for some form of fusion, because we are having a static tree that we are writing down that is built up, and then we are immediately consuming again using lookup. But fusion is not built into the compiler in some magic way. It is usually implemented by means of rewrite rules, and these rewrite rules are difficult to set up, and there are rewrite rules set up for list functions, for the basic list functions that we know, And there are some other examples out there, most prominently perhaps the text library, where fusion is applied. But certainly not for a random tree type that may even be domain specific in a particular setting or something that we just defined. So, so we don't have fusion here. What if we nevertheless want to exploit somehow the fact that we have a static table? Are there options that we have? Let's look at the options that we have. So here is one option. We can hand unroll the calls to lookup, and then we end up with some code that looks like this. We get a nested case statement with calls to compare and dispatching to the appropriate cases. Now this is good code, right? I mean, from the perspective of runtime performance and from what we might want. And if we run this through the compiler, it's quite nice. But in practice, it's not a good option because, I mean, as I said, in practice, our tree is probably much bigger than this, and it may change over time, even though it's static, and then we have to somehow manually apply the lookup function or whatever algorithm we're currently dealing with in our heads, and we're no longer programming at the level of abstraction that we're thinking about the program. And it's very tedious and very error prone to do this. So let's disregard this option. So option number 2, whenever we hear static in Haskell, we tend to say, well, types, right? I mean, our type system is static, and everything that has to do with the type system is done at compile time. So let's just move everything to the type level, right? So let's promote the BST type to a data kind, and then, well, lookup was a function, but let's just turn it into a type family. But then lookup takes 2 types, like a promoted number and a promoted tree. But where do we get the promoted number from? Because that one was supposed to be available only at runtime. Oh, well, that's not really a problem because there are ways to convert normal numbers into type level numbers using some sort of parsing function, something like sum nat val or something like that. But nevertheless, everything is getting quite complicated. We have to move to a completely different way of writing down things. And actually, there is still this lingering question, will it actually even end up being more efficient? That is not quite as obvious. Every once in a while, these type level transformation encoding tricks that we're applying, they come with their own overhead that we're introducing. And it's not immediately obvious, at least, that this will actually end up with the code that we would like to have. So I'm generally quite fond of type level programming, but in this talk, I think it's not the right solution, and let's disregard the solution as well. Now, there is also template Haskell. Template Haskell goes back to a Haskell's workshop paper from 2002 by Tim Sheard and Simon Peyton-Jones. And it's a meta-programming system for Haskell and can be used to generate whatever code we want, essentially. It's immensely powerful and a very nice system, but it also has quite a negative reputation. And I'm not going to go too much into it in this talk in how far this is deserved, but nevertheless, I mean, code that is written in template Haskell, it tends to be low level and difficult to maintain because you're often building up stuff by means of referring to the Haskell abstract syntax. And the Haskell abstract syntax, or at least the GHC abstract syntax, is not static. It changes over time. So the maintenance of this kind of code is often bad. And also, many patterns that arise, they do things like executing I/O effects at compile time or reifying parts of your code. So there is a certain amount of danger in there. But most of all, it is untyped, and therefore it's actually quite difficult to use. So if we were to write code that was somehow generating the right code for our lookup function, we would still have to externally document what type this code has so that users of that code would know how to use it or in which situation to use it. And so it's not obvious, right? It doesn't feel quite as direct as many other things. Nevertheless, it has good uses and it is widely used, and its primary use case, I would say, is eliminating all sorts of boilerplate code, so to have to write less code. But it is relatively little known that there is a variant of template Haskell in GHC that's called typed template Haskell, which is actually much more limited than template Haskell. And I'm going to argue that that is a good thing. So this actually goes back even further than template Haskell itself. It goes back to a Pepham paper from 1997 by Valitaha and Tim Sheard, which introduces MetaML, which is a typed staged functional programming language. And much later, in 2013, but nevertheless quite a few years ago, Geoffrey Mainland has implemented this essentially for Haskell on top of untyped template Haskell. And there is no paper about this, but a blog post and a GHC user guide section. But perhaps it's the fact that there is no paper that it has gone surprisingly under the radar, and not many people know about this. The other argument may be that, well, if it's just much more limited than template Haskell, how can it possibly be any good? But that's a surprising argument for Haskellers, because I mean, we are usually very fond of types, and we're arguing that functional programming in a statically typed language, despite all the restrictions that we're dealing with explicit effects even, right, that can be liberating because we have so much more that we can rely on while writing our programs. And exactly the same arguments apply to typed template Haskell. So first of all, it's typed. It encourages and provides a high-level interface. You don't usually run I/O at compile time. You don't usually reify definitions from other modules and so on and so forth. So you have much less low-level introspection going on. It does never generate top-level declarations. It only generates expressions. And these restrictions, they make it quite nice to use. And nevertheless, if you need it, if you really, really need it, it's built on top of normal untyped template Haskell. And there is an escape hatch so that you can access the power underneath in situations where you really need it. And that you can compare to like unsafe perform I/O and Haskell actually being useful, despite the fact that it is very rarely used and there are not very many legitimate uses. But nevertheless, it can be quite useful. And in the same sense, this way that type template Haskell is built on top of normal template Haskell is occasionally quite nice. And the primary use case is different because of these different features. The emphasis is different. The emphasis here is not so much to save writing a lot of code by sort of simulating language constructs which we otherwise might not have, but the use case here is really reliable performance, right? Getting well-performing code without having to rely overly much on GHC's optimizer. So how does type template Haskell work? It provides two staging constructs, as I call them. So two main language constructs. And they both work on the expression level. And one construct is called quotes. So you can take an arbitrary Haskell expression and surround it in these quote constructs. And if the Haskell expression had type T, then the surrounded expression will have type code of T. And the effect is that we're not intending to evaluate this expression, but rather build just a piece of code out of it to build an AST, essentially, that will be generated for us in exactly the form that we write it down. And then there is some form of anti-quotation, which is called splicing, which goes the other way around. So if we have a piece of code, we can splice it typically into a quote. And the idea is that that re-enables reductions and inserts this piece of code that we have there at that point into the AST that we're building. And the special case of this is that if a splice does not occur inside another quote, but on the top level, then it inserts the AST we're building, the expression AST, directly into the current module, so we can like have a generated expression accessible for use in the current module that we're just writing. So let's try to apply this to our lookup binary search tree example. So this is the function lookup that we started with. That is exactly the same function that we had before. Now, this function in its stage form is supposed to ultimately be invoked as a top-level splice and therefore to run at compilation time. So we're going to invoke lookup to a statically known BST at compilation time. So because it's run at compilation time from the perspective of this function, everything that is statically known does not change in type, but everything that is dynamic, everything that we only know at the ultimate runtime of the overall program, is stuff that is of type code. So if we look at the change type signature, most substantially this integer, which is a dynamic argument, which we don't assume to be available at compile time, gets type code of int rather than int. And because the ultimate result depends, of course, partially on this dynamic information, the integer, the result is also going to be code of maybe A. And now here we have a little bit of a choice. What do we do with the elements of the BST? We could leave them BST of A, but we could also turn them into BST of code of A. I'm doing it like this because I want to make sure, or I want to emphasize that the only thing that we really rely on to be available statically is the spine of this binary search tree and the keys of the binary search tree, which we didn't parameterize over. But we are not actually relying on the values of the binary search tree to be available. So let's operate on the assumption that the type signature is like this. Now the left-hand sides are still okay, because only the only thing that changes is some of the types of the things that we're matching on. This I here is of type code int now, and this A here is of type code A now. But otherwise we're fine. But on the right-hand sides, we're no longer having correct types. So this nothing here is not type correct because we have to produce a code of maybe A, but we can simply quote the nothing. And in the node case, we are producing code for this case statement. So we are surrounding the whole case statement in a quote, and we do this comparison and these three branches. But there is still something wrong, because if we look at this first argument of compare, we have this I here in the original version, but I is now of type code of int. And we are here inside a quote where we expect an int to pass to compare. So we can just splice the I in order to get the code for this integer inserted at this point. So that just works fine. And now the situation for the j is also interesting, because j is of type int, and we want to produce code of type int. So inside the code, we want to have something of type int here as well. But these are at different levels. So this is a static int, and here we want to build an AST of type int. And the idea is, of course, that if the int, for example, represents 42, then we want to actually insert the integer literal 42 into this code. So evaluate whatever j is referring to an actual concrete integer value and insert the literal into the code. And this operation is available as a lift typed in type template Haskell, which essentially takes an A to a code A. And the idea is exactly to evaluate this A and produce code that represents that value of type A. And integers are an instance of this. So if you want to be explicit, you can write it like that. Actually, GHC does allow us to write just J and then does this translation itself. But I find it more enlightening to be explicit about this. And now the rest is relatively simple. We splice the recursive calls to lookup, and we splice the A, and that's it. So this can be unusual at first, but if you do this a couple of times, it's not that bad. And in particular, if you look at it and just strip all the staging constructs, you get back the original code. So in its most simple form, staging is nothing more than essentially annotating the code with additional information about what is supposed to happen when. And stripping out all that information yields back the original code again. In more advanced use cases, we can do more, but that's the basic aspect. And then how to use it? Well, if we just mildly have to change our table because all the values are now of type code of strings, so we quote these strings. And then our specialized lookup table contains a top-level splice where we apply lookup to the statically known table. And now, if we look at the core again, it's much longer, and I mean, it's perhaps a little bit hard to read, but this is what we wanted, because if you look at what's happening, lookup table is unboxing the integer argument and then calling this worker lookup table. And then the very first thing the worker lookup table is doing, it's doing a comparison between the integer argument and the unboxed integer 5, which is the root element of our static tree. And then depending on what happens, it might also compare with 7 or with 3. And it's really just this nested case statement that we had seen when we were writing the hand unrolled code. And indeed, this is equivalent, exactly the same, apart from sort of numeric identifiers that the compiler assigns to the hand unrolled code. And it is not relying substantially at all on GHC's optimizer. So that is what I mean by reliable, right? It's dictated by the semantics of type template Haskell that we get this code. We don't have to trust that the compiler is implemented in a particularly smart way, even though it is. And that's still good, because it also means that the code is still subject to optimization. So if there are subsequent optimizations that we want to rely on, we are not preventing anything from happening. Okay, let's look at another example in slightly less detail as I discussed the first example, but just but still related, and that's routing in a web server. So if you consider an API of a web server, then you may have a long list of endpoints that are available. And sometimes there are captures, as I'm writing here using this colon notation. But one common aspect is that many of these prefixes are actually similar to each other. And if you naively route requests by essentially just like checking whether the first route matches or the second route matches or the third route matches, you're getting quite an inefficient router. And you can do much better by going to some kind of tree-like structure again, where you look at these path components separately and basically just look at the top level path component and see, like, is this login or is it language? So I dispatch here or there, and then you continue looking at all the routes that start with language and so on and so forth, right? So that suggests that we should build up a tree of routes and use that for routing. But then we have some sort of tree structure again, and that is lingering at runtime, even though it is usually statically known. And we could just assume that the compiler might optimize it completely away. So in that sense, it's quite a similar situation to what we had with the lookup and the binary search trees. So we are interested in efficient dispatch. And let's just briefly look at a very, very drastically simplified scenario where a route is assumed to be some kind of list-like structure where there can be two possible components. A path component of a route can either be static and require a particular piece of text to be there and then continue with the route, or we can say we want to capture the entire component and then continue with the route, and then we finally end. And then we have an abstract type router, and we have two ways to construct a router. Either we can construct a router for a particular route and map it to a handler, or we can combine routers using a semigroup operation that basically says this or that. And then we have requests that are assumed to be just lists of texts, and we have handlers that are taking a list of text, but this is just supposed to be all the captured elements in the route, not the entire request, to the response. And the response, we, for simplicity here, also just assume to be text. I mean, in practice, it would be IO of some results type, right? And then we finally have a run function that takes a router and a request to a handler. Okay, so if we want to stage this, right, then the idea is that we first, in the first phase, we just build up a list of pairs, or you can think of it as a map, a dictionary from routes to handlers, where we want to know the routes statically, but we don't care about the handlers, so they can be code of handler. And then that has an obvious semigroup structure by just concatenating these lists. And then we can combine or we can translate such a router, a combined router, into such a tree-like structure where we, as I said, we look at the top-level path component and dispatch to another root tree. And we have another thing for storing all the elements that want to capture the top-level path component. And we have potentially a handler for an endpoint that stops at the position where we just are. And then we can write a function build root tree that goes from such a router to a root tree, which is supposed to run completely statically. And indeed, these root trees are supposed to be existing just as compile time, as a helper, as a high-level helper for us of expressing this idea of static routing. And then finally, we can write an interpretation function that goes from a root tree and a dynamic request and a dynamic list of accumulated arguments for that request to a dynamic response. And this routing function will produce a nested case statement again that goes to these request components one by one and uses a helper function here that ultimately matches these individual path components one by one using a nested if then else statement. So I'm not going to explain all of this in detail due to time, but again, this is not very deep, right? I mean, this is cluttered up by the staging annotations, but it is very close to code that you otherwise would write yourself as well. And in fact, it is not even perfect yet, because of course we are doing this chained equality test per path component here, where we are still like comparing entire strings. We could easily make it even better by sort of doing a try-like structure that would do the string matching in a more efficient way as well, without needing a completely different approach. And if we run this root via tree function in a top-level splice in the end to on a completely statically known router, we will again get a nested case statement with nested if then else's and all this code reliably produced at compile time without any overhead and without having to rely on the optimizer in any particular way. Okay, so what are other applications of staging? So there are quite a number of them actually. So one nice area are things that can be fused, pipelines. So you can think about things like conduits or pipes, right? Or even just composing list functions. Usually the nature of the pipeline is static. You know that you have a fold after a filter after a map. You may not know exactly what the input list is. You may not even know in all cases what the argument functions are, but you know that there is this kind of sequence and you can exploit this and produce reliably fused pipelines. Parsing in all forms is an excellent application for staging because in a way this routing that we've seen is a simple form of parsing, but in general in all sorts of combinator parsers, you're essentially writing down the grammar, and there is some overhead introduced by the parser combinator machinery itself, but then in addition, you're also having a hard time doing certain kinds of static analysis or pre-analysis on the grammar, such as what are the first sets or the follow sets of all the non-terminals in your grammar, or does a certain parser accept the empty string or not? And if you move to a staged setting, these things become not only more explicit, but also much more easy to exploit in an efficient way. If you consider templating languages or any kind of serialization or printing, there's usually just a few holes that you plug in, and a lot of stuff that you're composing is actually completely statically known. So there's no need to always reevaluate or recompose all the statically known aspects of your templates on every invocation. You could exploit that you know these statically and evaluate them at compile time. And finally, generic programming is a good example because we have some often quite involved code that moves to an intermediate representation. And this intermediate representation is just for administrative purposes and introduces quite a bit of overhead. But if you specialize to a specific type, you can get rid of it all. And so that's quite nice. My conjecture is that nearly any EDSL can be staged and can benefit from staging. And this promises much better and more reliable results than the standard approach, that is to just rely on inlining specialization and rewrite rules, which experience shows is, I mean, GHC, don't get me wrong, GHC is an incredibly clever piece of work, and the optimizer is fantastic. But nevertheless, often if you change compiler versions, if you make your program slightly bigger, all these optimization techniques, they rely on heuristics and thresholds, and they are brittle. Ultimately, if you really rely on something to be optimized away, there are always bad surprises along the way. And having something that is predictable, like the staging, is promising to be better. Okay, so we're coming to the summary. Basically, if you want to stage something, there are 3 phases, of which I've only shown the first 1.5. So the first is to remove the immediate overhead. That is usually achieved by doing just an annotation of the original program. The second is to exploit deeper knowledge by performing additional static analysis. That is stuff like moving to this tree-like structure in the routing setting, which you wouldn't have had to done in the first place. Wouldn't have had to do in the first place, but you can do it. And the third would be to make an even more fine-grained distinction between static and dynamic data and work with partially static and partially dynamic data. But there's quite a number of things possible. I want to briefly point out a number of other interesting concrete applications and papers, so that if you want further reading. So there is an upcoming Haskell symposium paper this year on applying staging to generics SOP, which is a generic programming library by Matt Pickering, me, and Nick Wu. And so that is, I think, quite cool and promises to be really an improvement. There is also at ICFP 2020, there is a paper by Jamie Willis and Nick Wu and Matt Pickering on stage selective parser combinators that shows how to apply staging to parsing. And then there are other cool applications, such as doing constant folding and exploiting algebraic laws on algebraic structures by Jeremy and others, Jeremy Yallop and others. And there is a paper by Oleg Kizelyov and others for Meta OCaml that is explaining how to apply staging to stream fusion. And a colleague of mine, Oleg Grenus, is actually currently working on some Haskell version of some of these ideas. So stay tuned, there will be more to come. Now, the conclusion of the talk is that staging can ensure code that is obviously performing well. You can avoid the unpredictable, or in the case of recursive functions, even unavailable features of Haskell's optimizer. And you can remain at a high level. You have to do some extra work, but you can remain at a high level of programming. And you can even perhaps go to an even higher level, because you no longer have to be afraid of introducing overhead. And in principle, all of this is available now. In practice, there is quite a bit of stuff that Matt Pickering has been recently working on improving. And some of this is also the topic of this staged sums of products paper that I mentioned, that is to be talked about at the Haskell Symposium. But one main point here is that many of these issues with the current implementation of staging in Haskell can only be found and eliminated if staging is actually being used. So use more staging. And I think there is a lot of potential here that is still undiscovered. Thank you.